Ever had the feeling that your error handling and your app's flow could be simpler? Then railway-oriented programming might be exactly what you need. It's an approach introduced by Scott Vlashin, and it models your application logic as a set of rails. One for success, one for failure. The idea is to make error propagation as clear as the normal execution path, with minimal complexity. In this video, we'll visualize and evolve together the structure you see on screen, side by side with the code. We'll use a simple example with operations such as validation, error handling, API call, business check, and data transformation. We'll bring railway-oriented programming to life using the Effect library, a functional programming library that helps us write expressive and understandable code, following principles that can be applied to other programming approaches. Before diving into the code, a quick word about Effect. If you've worked with promises, you already know the idea. One rail for success with .then, and another for failure with .catch. Effect builds on that concept, but takes it a step further. Each effect's signature includes the success type, the error type, and the dependencies required for its execution. To make things easier to follow, we'll stick to the familiar terms then and catch, while enjoying the clarity and structure that strong typing brings. All right, let's lay down the rail and jump into the code. We're working in TypeScript, the language used by the Effect library, but the ideas we're exploring here apply in any language. Let's take a look at what we have. An input with an ID key and an initialization function that calls an anonymization function. In this demo, anonymization means fetching a user through an API and modifying the user's data to make them anonymous when certain conditions are met. Right now, if we peek inside the function, it just logs the input and returns it unchanged, currently typed as unknown. On our diagram, we lay down a green rail, representing the input flowing through untouched. And if we run the code, the console shows a simple log of our input. Now, let's turn this anonymization function into an effect. We do this by wrapping its contents in a function that always produces a successful effect. On the diagram, we add a red rail next to the green one to represent the error path that every effect has, but it's not connected. No error can reach it. Everything will always run on the success path. In the code, let's update the function signature. It's an effect that returns unknown, throws no errors, and has no context. To make this effect run, we also need to update the initialization function, adding the necessary instruction to trigger it. Why do we need this? An effect on its own is just a description, a blueprint of what should happen. Nothing actually runs until we explicitly ask for it. This instruction bridges the effect world with standard JavaScript, converting our blueprint into a promise that executes. Now, when we run the code again, we get the same log in the console, but this time, it comes from an effect. Now that this setup is complete, let's swap out our simple logging function for an input validation function. The goal here is to stop working with an unknown type. To do this, we'll use a function provided by the Effect library called validateUnknown. If the validation succeeds, we get the parsed input, and execution continues down the success rail. If the validation fails, execution switches to the error rail, with a parsing error produced by validateUnknown. Back in the code, to match the diagram, all we need to do is replace our success log effect with validateUnknown, and provide it with the schema and the input as arguments. To get a simple but accurate understanding, let's look at a naive implementation of this function. It's a standard try-catch that returns a success if parsing succeeds, and a specific failure otherwise. This generic mechanism is what's captured in validateUnknown, which we can provide with any argument. If we take a closer look at the schema, we see it's a simple object structure, which has the advantage of serving both as a runtime validator and for static typing. Once that's done, all that remains is to update the function signature, so that it correctly reflects the behavior of validateUnknown. Now that we have a validation blueprint that divides the flow in two, let's add a logging function that receives both states. To let the outputs flow through, we'll use a pipe. It lets each instruction pass its result implicitly to the next line. Now that the results flow through the pipe, we handle them with a match function. It takes an object with two keys, one for the green rail and one for the red. Each one has its own pretty logging function, customized for its output. Since these functions now capture both outcomes in their signatures and make the end of our application explicit, we can remove the old anonymization function signature. It's now out of date. If we run the code and look at the console, we now see a success log, still showing the input, but this time guaranteed to match the validated structure. And if we go back upstream and with this schema now enforcing our output shape, when we alter the input at runtime, we get a parsing failure, just as expected. We've reached a milestone. Our first effect is in place. From here, we'll extend the rails, piece by piece, starting with the red one. Right now, our parsing error is purely technical. It doesn't reflect the step it represents. What we want is to add a new segment to the red rail, one that transforms this raw parsing error into a determined failure. The green rail continues unchanged. To indicate that we're acting on the red rail, we'll use the instruction catch. And to define what happens next, throw. When the flow hits this path, we'll catch the error and throw a failure, invalid input. That will become our new output. And that's exactly what we'll do in the code. We add a function called catchThrow. It catches any error from the previous step and rethrows it as the predefined failure we pass in. Again, a naive implementation to represent this mechanism would be to throw a different exception, a business one, inside the catch of the validation failure. The catchThrow function simply isolates this mechanism, which allows us to insert it differently into the flow in a way that brings invalid input business requirement into the light. Let's take a look at its definition. It's a class invalid input, which extends failure with a specific message, covering the case of a technical parsing error. And that's it. All that remains is to update the signature of the red output. And when we run the code, we get the same failure, but it's no longer a generic parsing error. Now let's add a few computations on the green rail, starting by using the validated input to trigger an API call to fetch a user. We'll use an HTTP client, which on success returns a response and on failure produces an HTTP client error. This time, it's the then instruction that expresses the intention to act on the green rail, and try informs us about the shape of the action, meaning it has at least one failure case that can flow onto the red rail. Back in the code, we can again simply add a then try function, taking as argument the function to execute only on the green rail, receiving the validated input. Again, a simplified example of the then try mechanism can help us understand what it does. We simply build the railway switch by wrapping the execution of a callback in a try catch. We are just factoring out flow mechanics around the actions that are at the center of attention in our pipe. And at this step, that's fetch user. For now, this function is just a placeholder, which will evolve next so that it matches our current diagram. For now, let's provide our HTTP client in the execution context. Back in the initialization function where we convert our effect into a promise, to be able to work with a context, we must define a scope that marks the boundaries of our context usage. We do this by adding a scope instruction attached to our anonymization function. Now every piece of context will automatically expire when we leave its scope. Then all we need to do is provide an HTTP client layer from the effect library, and it will be available everywhere in the code. We can now use it back in the fetch function. In this case, simply call get with the external API URL as argument, and we are done. As usual, we update the function signature with the outputs documented in the HTTP client to describe the end of the rails. You'll notice the red rail now combines two possible failure cases that can reach this point. Looking at the diagram, we can see how these failures flow. If validation fails, we immediately move to the red rail before the API call. But if validation passes, we continue forward where an HTTP error might occur during the API call. While only one failure can happen at a time, both share the same terminus on the red rail. And regardless of which path we take, the entire pipe is always executed from start to finish. And that's why we need to keep our terminus clean and avoid receiving technical errors like this HTTP one directly. So just like we did earlier for the input validation, we'll wrap it in our own failure. We simply pipe the same catch throw instruction again, and we give it a dedicated failure. Then we update the function signature to reflect this new output. On the diagram, we add it to the red rail, and that's it. No need to modelize this sub-step in the main flow. Finally, the content of the response is stored inside its body, so we need to access it and make sure it matches the shape of a user. For that, we'll use a familiar function similar to validate unknown, called validate body. In the code, since I'm on the green rail working with an action that connects to the red rail, again the function then try will correctly chain our response body validation against a user schema. To understand this mechanism, we can refer back to how we validated the input. It works the same way with one additional step upstream to handle the HTTP envelope. Whichever step, when validation fails, a technical parsing error is emitted and will reach our failure wrapper. So we have to update it to maintain both type safety and documentation. From the outside, nothing changes on the red rail. Get user failed just has two possible failures. But the green rail now outputs a user. We update the signature accordingly, and when we run the code, we get a valid user with just a few lines of code. Perfect. But here's the thing. We shouldn't anonymize a user who's already anonymized. We need to make sure we're only processing users whose type is not anonymized already. Let's model this business rule on our diagram. We'll add a validation step on the green rail that examines the user's type property. If the user is not already anonymized, we continue forward on the green rail. But if the user's type is anonymized, we'll flow to the red rail with an already anonymized failure. Once again, to continue on the green rail, we use the then instruction. But this time, since we're implementing a business validation where we decide when to emit the failure, the instruction is throw if. This allows us to conditionally flow to the red rail based on our business logic. Time to implement this in the code. Right after the API call, we simply add a then throw if function. It takes two arguments. The predicate user is anonym, which is just a property check, and the failure already ain't on him. And that's all we need to do. Once more, a simplified version of this operator helps us understand the mechanism. It's the same structure we've seen before. This time, success and failure depend on the predicate result, along with the failure to emit if the check fails. Now, if we look at the failure definition, we can see it follows the same structure we've seen before. Except this time, the technical error property is empty, since this is a business failure, not a technical one. Back in the main flow, we update the function signature to add this third failure case alongside the existing ones on the red rail. Now that we've validated the user isn't already anonymized, we can proceed with the actual anonymization process. Let's model this on our diagram. This time, we'll handle two transformation steps in sequence. First, the anonymization step on the green rail, producing an anonymized user. The red rail remains unchanged, flowing past this step since these transformations don't connect to it. Next, the final output creation step, following the same principle. The green rail transforms our anonymized user into a bus event, while the red rail continues carrying our previous failures. To chain these transformations, we use the then instruction on its own. No try or throw if this time, since these are simple transformations that stay on the green rail. Back in the code, let's implement the first transformation. We add a then function with our transformation logic. Let's take a look at it. It creates a new user by duplicating the current one with some alterations. It's guaranteed to be valid since this make function is a user type constructor, as you can see here. A type that was inferred from the user schema we used earlier during body validation. This way, our schema remains the single source of truth throughout the entire flow. After that, we chain another then function to wrap this anonymized user into a bus event object, with a topic property containing our topic name and some relevant key value from our user data and process, using the same constructor strategy. By the way, this then function simply wraps the callback result in a success effect. It never fails. It's straightforward enough that we can skip the simplified version this time. Finally, we update the function signature to reflect this last modifications. The green rail now outputs a bus event, while the red rail still carries our 3 failure cases unchanged. And that's it. 2 simple transformations chained together with then producing our final output. Now when the code runs, mission accomplished. We reach the end of our pipeline. Before we wrap up, let's see how easy it is to extend this code with a few relevant examples for our use case. First, let's add a business constraint on the input. We can do this easily. Back in the schema, we add a constraint. For example, a maximum length of 3 characters for the ID. This approach is simple, well-centralized, and doesn't disrupt the existing flow. Second, in the fetch user function, let's move the API address into an environment-based configuration. To do this, we go back to the root level. There, we inject our configuration into the context. Now it's available everywhere. We can access it where needed, just like the HTTP layer. The difference is we invoke it manually since it's a custom injection, but the principle remains the same. While we're at it, let's add a timeout and a retry. We insert them right after our call using the tools from the Effect library. Since timeout is now a new possible failure, we document it alongside the existing ones. And finally, let's fix an implementation error. If we change the ID to one that doesn't exist and run the code, we get a parsing error. The program tries to process an empty HTTP response. A not found error would be better. In other words, when the call succeeds but finds nothing, we want to throw a specific error. In code, this means adding then throw if status not found, user not found. This error also needs to be documented in the same place. And that's it. We could make other modifications, but for our use case, the essentials are here. Of course, there are many critical scenarios in software engineering we haven't covered. The Effect library provides numerous tools to handle concurrency, streams, and much more. If you want to try this library, keep in mind that some functions we've seen together were crafted from Effect functions specifically for this video. Others were renamed to create this nice correspondence between the 2 sides of the screen. Ultimately, there are countless ways to build this same program. The choice you make matters little as long as you establish a strong link between the code and a structured representation of the flow that anyone can easily understand. That's where the true essence of railway-oriented programming Effect lies.